Okay, now in the last section of his paper, Turing then uses this, this example of an undecidable problem to show that the problem we started with, namely the logical decision problem, is unsolvable. To remind you, we had a formal language of logic that was developed or brought sort of to its sort of the height of was finished, so to speak, in the 1920s by Hilbert and his students. And Hilbert formulated the question of whether there could be a mechanical procedure that would test whether a given formula in this artificial language can be proved from a number of other formulas in this artificial language. If there were such a procedure, then we would say that the decision problem is mechanically solvable. And had there been such a procedure, right? So if you could come up with such a procedure that would tell you, given any sequence of any family of axioms and a candidate theorem, whether it is in fact provable from these axioms, right? Then we would have mechanized mathematics and large parts of physics, right? Because all you have to do is, whenever you want the answer to a question, say in geometry or thermodynamics, right? You write down your question as a sequence of symbols in this formal language, and then ask your Turing machine, can you prove this from the axioms of geometry or the axioms of thermodynamics or the axioms of piano arithmetic and so on, right? So here's an example, for instance. The axioms of number theory were first given by Dedekind and then formalized by Peano. They're now called the Peano axioms of number theory. And then, for instance, you might be interested in whether Lagrange's theorem is true in the natural numbers, right? So Lagrange's theorem says that every natural number can be written as the sum of 4 squares. Now, all you have to do is translate that proposition into the formal language, and there's the formula that in sort of one standard formulation of that language says that, right? For every number x, there are 4 numbers, y1, y2, y3, y4, such that x equals y1 squared plus y2 squared plus y3 squared plus y4 squared. Now, if you're interested in whether that's true in the natural numbers, just ask, is that a consequence of the Peano axioms? Right? So that's what the decision problem would do, or a positive solution to the decision problem would do, if it had been solvable. Now, the logical decision problem can be actually reduced to the question whether a single formula in the formalism, in Hilbert's formalism of logic, can be proved from the axioms of logic alone, simply because the question of whether formula B follows from some axioms A1 through AN reduces to the question of whether a particular formula of that form A1 and dot 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 and AN arrow B, whether that's a logical truth. So as I mentioned, there were a number of partial successes. Lots of people were working on it, so there was grounds for optimism that this would have a positive solution, and that's what then in 1936 Turing showed can't be done. And the way he did that, I will spare you the details, but the basic idea is simply that you can think of the execution of a Turing machine, or what happens when a Turing machine runs, say on an empty tape, right? You can think of that as a domain that you can axiomatize. You can write down a bunch of axioms that tell you what the Turing machine does in its execution. So you can write down a system of axioms with a number of primitives, right? So for instance, these primitives might tell you this is a configuration of a Turing machine, or it's the square of the tape, or it's a state of the machine, or it's a symbol that might appear on the tape, and then you have a bunch of relations, right? So for instance, a configuration of the Turing machine might stand in relation follows after to another configuration of the Turing machine. Namely, whenever the Turing machine is in that configuration, the next one is the one that it follows after, or that follows after it, right? Or the relation between a configuration and a symbol, which holds if the Turing machine, when it's in that configuration, reads that symbol on the tape, and so on. So those would be the primitives of the axiom system, and then you write down a number of axioms. Finitely many, because you're, the only things that you have to talk about are the instructions in the program, right? So for instance, if your program contains the instruction, when you're in state I and reading symbol Sj, then write symbol Sk, go right, and switch to state M, then one of the axioms is a fact about the configurations of the machine and what it does in certain configurations. For instance, whenever T is in a certain configuration in which the state is I, it is scanning square S of the tape, and the square S contains the symbol Sj. Then in the configuration that follows after it, the machine is in state M, the square S contains symbol Sk, and T is scanning the square that's to the right of square S. Right? Then we need a few other axioms, right? Other axioms that ensure that nothing happens on the tape where the Turing machine isn't working, right? So that the symbols don't change arbitrarily somewhere in the tape. And then the question of, for instance, whether the Turing machine T ever prints the symbol 0 is just the question of whether that statement eventually, in some configuration of the Turing machine T, some square of S contains the symbol 0, right? Whether that proposition is a consequence of the axioms which completely describe the operation of the Turing machine. Right? Now, if the Turing machine, if the decision problem in its general form were solvable, then there would be a Turing machine which tells you that, which tells you whether or not this proposition follows from the axioms that describe the execution of the Turing machine. And that Turing machine can then, of course, be used to solve the question or to answer the question of whether the Turing machine T ever prints the symbol 0. But that, Turing has shown earlier, can't be done. There's no Turing machine that tells you, given the code of a Turing machine, does that Turing machine ever print the symbol 0. Okay? So that's Turing's solution, negative solution to the decision problem.